So in this video, I'm going to show you the second part of the Riemann's rearrangement theorem. Uh, Let me just first explain what the theorem itself says, then I'll give you a little bit of an idea about the how proof will go, and then I'll show you the actual proof. Now in this case, the proof that I'll show you, you'll see that it's actually a relatively longer proof. It's also a little bit complicated. So what I'm also going to do at the very end is I'm going to, in the description box below, I'm going to upload a PDF in which I have typed up the entire proof for both the first part of the Riemann's rearrangement theorem that I showed in the previous video and the proof for this second part that I'm going to show you in this video. So if you ever want to refer to the proof, you can always access that PDF. Okay, so first of all, let's just see what the theorem says. So the second part of the theorem says let the summation from n equals 1 to infinity be a conditionally convergent series. So what does it mean for a series to be conditionally convergent? There are essentially three ways you can think of, or two ways you can think of it, both of which are equivalent. They are equivalent ways. They essentially mean the same thing. The first way is that the summation from n equals 1 to infinity of a of n converges, but the summation from n equals 1 to infinity of the absolute value of a of n diverges. So it's essentially a sequence that converges, it's essentially a series that converges, but that diverges when each of its terms are summed up in absolute value. So that's one way to think about it. The other way to think about it is a conditionally convergent series has a bunch of positive terms, or infinitely many positive terms and infinitely many negative terms being added with each other. And the other way is that the other way to think about it is that the summation from n equals 1 to infinity of only the positive terms diverges to positive infinity, and the summation from n equals 1 to infinity of only the negative terms also diverges, and of course that will diverge to negative infinity, but the summation from n equals 1 to infinity of a of n converges. So this converges, but so if you add up all the positive terms and the negative terms with each other, the summation will converge, but individually the sum of all the positive terms diverges to positive infinity, whereas the sum of all the negative terms diverges to negative infinity. So both of these are equivalent ways of thinking about what conditionally convergent series are. Okay, so okay, let's move on. So it says that for any conditionally convergent series, so we have defined this to be just any conditionally convergent series, and then the theorem states that for any real number, there exists a permutation. Once again, if you don't know what this notation means, I would ask you to go back to the previous video. It just means that a different permutation, a different way of ordering up the same numbers. So for every real number, there exists a permutation of the set of real numbers, or of the set of natural numbers, such that the summation from n equals 1 to infinity of a of alpha n is equal to s. So what this is saying in simple words is that if you give me any real number, I'll be able to rearrange the terms of this series or of the sequence a of n and add them up in some rearranged order such that the summation will converge to the real number that you've given me. So for example, you can give me the number 1, and then if as long as the series is conditionally convergent, I'll be able to rearrange the sum, or I'll be able to rearrange the terms in the series such that their sum is 1, or its sum converges to 1, to be more precise. Okay, so this is the theorem, and why is this theorem so important is because it shows us that conditionally convergent series are not commutative. In other words, if I add them up in in some order or in different orders, I will get different sums. In fact, this is only part. So I'm saying that this is part 2 of the Riemann's rearrangement theorem, but there is actually another part to this which says that there also exists a rearrangement in which the summation goes all the way up to the summation of n equals 1 to infinity of a of alpha n is actually infinity, and then there also exists another rearrangement in which the sum goes to negative infinity. So I mean, you can also rearrange the series such that it diverges, but I'm not going to go into that over here. So now what I want to do next is basically give you guys a general idea about how the proof is going to go. And then once I've given you that general idea, I'll ask you to pause the video and see if you can write a formal proof on your own, a formal proof on your own. So here's the general idea behind the proof. So this is the general idea. Okay. So the way the proof is gonna go is, let's say, so I'm gonna create a graph over here. Okay. So let's say that this is my graph, and let's say that the number I want to create is s, and this is s. It could be any number. It could be 10, 11, 12. Doesn't really matter what the number is. Now, what I'm going to do first, notice that since the summation from n equals 1 to infinity of a of n is a conditionally convergent series, by definition of conditional convergence, I know that the summation from n equals 1 to infinity of only the positive terms of the sequence is infinity, whereas the summation from n equals 1 to infinity of only the negative terms is negative infinity. So, in other words, it must be true that I have enough positive terms such that if I add them up, I can obtain s. Well, because this sum goes to infinity, and assuming that s is greater than 0, I must have enough terms in the sequence such that when I add them up, I can obtain s. So what I'm going to do, or well, I obtain something larger than s to be more precise. It might not be the case that I get exactly s, but it's always going to be possible for me to obtain something greater than s, as I have enough terms to create infinity, for example. Okay, so what I'm going to do is I'm going to take the least number of terms from the positive sequence, or from the sequence of positive numbers that are found in the sequences of n, such that if I sum them up, I just exceed s. So let's say that I require 10 terms, and when I add those 10 terms up, I exceed s. So let's say that if I add up the first 9 terms, I reach this point, but when I add the 10th term, I obtain something that is greater than s. So at this point, I'm going to stop. The next thing I'm going to do now is I'm going to take enough negative terms such that when I add these negative terms up to the positive terms that I've already added up, I'm going to get something that is smaller than s. So let's say that I require 3 such terms. So let's say when I added 2 terms up, I was right over here. And then when I added the third term up, I obtained something that was less than s. And now I'm going to continue doing this. And the idea behind the proof is that if I continue doing this forever and ever, eventually the sum will converge to s. So it's going to look something like this. At each point, this is the new sum. At each point, the sum is going to get closer and closer to s, until eventually I can conclude that the sum converges to s. So that is the general idea. That is the general idea that we will use throughout the proof. That is, if we add a certain number of terms, I'm going to get something greater than s, then I'm going to get something smaller than s if I add enough negative terms to it. But that each time I, uh, exceed s, for example, I'm exceeding s over here, I'm exceeding s over here, I'm exceeding s over here, and so on. But each time I exceed s, I'm exceeding s by something that is smaller than the previous one. So let's say that over here I exceeded s by 1. Now over here I'm exceeding s by, let's say, 1/4. Over here I'm exceeding s by only 1/10, and so on. So each time and after each step, I'm getting closer and closer to s. So that is the general idea. So using this general idea, see if you can write a proof for this theorem, and see if that matches up with the method that I'm going to show you. So by now, I hope that you've paused the video and you've attempted this question on your own, attempted to write a proof. Now, if you didn't get the proof of this on your own, there's no need to worry, because this isn't a proof that's easy. It's actually a pretty complicated proof. Here's how this is going to go. Okay. First thing, always make sure that whenever you're writing a proof, you redefine all your variables. So first of all, I'm going to say let the summation from n equals 1 to infinity of a of n be a conditionally convergent series. So I'm going to assume it's conditionally convergent. That just comes from the statement of the theorem. And then what I want to show what I want to show is that for every real number you give me, so for every s in the real number, there exists a permutation. I'm going to use alpha instead. There exists permutation of the set of natural numbers, or this is another way of saying the same thing. There exists a bijective function that maps from the set of natural numbers to the set of natural numbers, such that the summation from n equals 1 to infinity of a of alpha n is equal to s. So in other words, for any real number you give me, there exists a rearrangement of the set of natural numbers such that if I add up my add up my add up my sequence s of n in that rearranged order, I will obtain s. Okay. So given that that is true, what do I do next? So first of all, I'm gonna say let s be any real number. So let s be a fixed real number. And for this case, without loss of generality, I'm going to assume that s is something positive. It doesn't matter if s is something negative. In general, the process will remain the same. Now, I'm going to be a little bit more precise because what I want to do is I want to differentiate the positive terms from the negative terms. So I want to say, well, this is the set of the positive terms that appear in the sequence a of n, and this is the set of negative terms that appear in the sequence a of n. And to do that, I'm gonna define it this way. I'm gonna say define a of n plus, which is the set of positive numbers that appear in the sequence a of n, to be equal to a of n plus the absolute value of a of n divided by 2. And I'm going to say a of n negative is equal to a of n minus the absolute value of a of n divided by 2. So for example, let's see what happens. Let's say that I have the term, let's say that a of n is equal to negative 2. Okay, so this is a negative number. Let's see what happens when I put it over here. So when I put it over here, I get negative 2 plus the absolute value of negative 2 divided by 2, and it's just changed to 0. So what this process is doing for the set of positive numbers, or when I'm saying a of n plus, is that it's if all the positive terms remain the same. So for example, if I pick a of n equals 2, for example, and I just put it in over here, I'm going to get a of n plus the absolute value of a of n divided by 2. This is just equal to 2 plus 2 divided by 2, which is just 2 again. So what this process is doing is that it's changing all the, for example, what this process over here does, or what this term over here does, is that it changes all the negative terms of the sequence a of n to 0, and it keeps all the positive terms the way they were. What this does, what a of n minus, what the formula that I wrote for a of n, or the negative terms of the sequence a of n, is that it changes all the positive terms of the sequence a of n to 0, and keeps all the negative terms of the sequence a of n the way they are. So this is just something, if you want to define the positive and the negative terms of the sequence a little more rigorously, this is how you are going to do. You're going to do that. It's not compulsory, but I mean, if you want to be rigorous, then this is what you should do. So essentially, what it is that what this does is that this means, or that is, that the summation from n equals 1 to infinity of a of n plus is the sum of the positive terms of a of n, and the summation from n equals 1 to infinity of a of n negative is now the sum of the negative terms of the sequence a of n. Okay, so this is just something that I've written down to be formal or to be rigorous. Now, one more observation. Note as this, the summation from n equals 1 to infinity of a of n converges conditionally. So since this converges conditionally, what I know is that the summation from n equals 1 to infinity of a of n positive is infinity, and the summation from n equals 1 to infinity of a of n negative is negative infinity. In other words, the sum of all the positive terms is infinity, whereas the sum of all the negative terms is negative infinity. And this is going to become important in a minute. Now, this is where the actual proof begins. This is where the idea of the proof that I just showed you is going to come in. So now I'm going to define that idea formally. I'm going to say next, I'll take in order. So in order means I'm going to take a of the first positive term first and then the second one afterwards and so on. I'm going to take in order the least number of positive terms from the sequence a of n plus, from the sequence a of n plus. Of course, this is where all the positive terms are going to come from, such that their sum exceeds s. So suppose we require x1 of such terms. So that's the amount of positive terms that we need in order for the sum to just exceed s. Now then what I can say is that the summation from n equals 1 to x1 minus 1 of a of n plus has to be less than or equal to s, because at this point the sum has not exceeded s. What we need the sum to do is to exceed s, and by assumption the sum exceeds s once I have added x1 of positive terms, and then this has to be less than the sum from n equals 1 to x1 of a of n plus. So in other words, what I'm saying is that if this is the sum s that I want to create, then once I have added up the first x1 minus 1 positive terms, I'm slightly below s, but once I have added x1 of the first positive terms, I have exceeded s. So that's the basic idea. That's what it's saying over here in simpler terms. And of course, I should recognize that this is always possible to do. No matter how large s is. So this is always possible. And why is it possible? As the summation from n equals 1 to infinity of the positive terms is infinity. So no matter how large s is, I can always do this, because by assumption, the summation from n equals 1 to infinity of a of n plus is infinity. Okay. So that's the first iteration. Now I have reached a point where I'm above s, where I've exceeded s. Now the next step, what I'm going to do is I'm going to say next, I'll add, once again in order, the least number of negative terms, from the sequence a of n negative, such that the resulting sum is less than s. So now what I want to do is I want to add the least number of terms in order from the sequence a of n negative, such that when I add when I add this up with what I've already added, I get something that is less than s. And let's suppose that I require y1 of such terms. So in other words, then what I'm gonna get is something like this. Then the summation from n equals 1 to x1 of a of n plus the summation from n equals 1 to y1 of a of n plus has to be, this is coming from the set of negative terms, has to be less than s, which has to be less than or equal to the summation from n equals 1 to x1 of a of n plus the summation from n equals 1 to y1 minus 1 of a of n minus, a of n negative. Okay, so why is this inequality true? Well, clearly from what I've just did previously, I know that the summation from n equals 1 to x1 of a of n plus is something that is greater than s, because once again, to give you a little bit of a visualization, if this is s and this is the sum of the first x1 minus 1 positive terms, then I'm going to stop whenever I have exceeded s, and we have assumed that we exceed s, when we have added up the first x1 positive terms. Okay, once I've done this, I'm going to start subtracting off terms. Now I'm assuming that I need an additional y1 terms to such that to make sure that my entire sum is now slightly less than s. That means if I've just subtracted y1 minus 1 terms, my sum is still larger than s. And that's what's happening over here. When I have added up y1 minus 1 terms, my sum is something that is still larger than s, or of course it's equal to s. It can be equal to s as well, because I'm only going to stop when I have a sum that is less than s. So y1 over here is the least number of negative terms I need, such that I can reach to a point that is lower than s, or that is smaller than s, which is why this inequality above is justified. Well, after this, once if you understand what's happening up till over here, the proof after this is actually pretty simple. Once again, I should recognize that this is always possible to do. This is always possible, as the summation from n equals 1 to infinity of a sub n negative is equal to negative infinity. So I will always have enough negative terms to go below s. Well, because the sum of all the negative terms is negative infinity, so I can always go below s, or reach a point or reach a number that is smaller than s. Okay. Now what I'm going to say is I'm going to continue this process. This process can be continued indefinitely. So if you just continue this process forever and ever, you can say that after n iterations, after n such iterations, I'll get the following. Okay, so this is what you're going to get in general. You're going to get that the summation from n equals 1 to x1 of a sub n plus the summation from n equals 1 to y1 of a sub n negative plus so on until you reach this n equals, well, y of n minus 2 plus 1, y of n minus 1 of a sub n negative. So this is just a way to generalize each step. X of n minus 1 plus 1 all the way up to x of n minus 1 of a sub n positive. This is going to be less than or equal to s, where s itself is going to be less than the following sum. It's going to be less than the summation from n equals 1 to x1 of a sub n plus the summation from n equals 1 to y1 of a sub n negative plus so on all the way up to well, this is going to remain the same. I'm going to get the summation from n equals x of n minus 1 plus 1 all the way up to xn of a sub n plus. So what I'm saying over here is this is basically, this over here is a general way to generalize each step. Notice that there are two steps, there are two iterations. One iteration comes from when I have added the positive terms, and then the second iteration comes when I have added the negative terms. So in general, whenever I'm adding the positive terms, I'm going to get something that looks like this. And whenever I'm adding the negative terms, so this is the first iteration, and whenever I add a negative term, it's going to look something like this. I'm going to get that the summation from n equals 1 to x1 of a sub n plus the summation from n equals 1 to y1 of a sub n negative plus all the way up to the summation from n equals x of n minus 1 plus 1 x of n minus 1 of a sub n plus shouldn't be a minus 1 over here, just x of n, because, well, this is where I'm at. And plus I'm going to add now a negative term. So it's going to be n equals y of n minus 1 plus 1, and then all the way up to y of n a sub n negative. And this, of course, will be less than s, which has to be less than or equal to the summation from n equals 1 to x1 of a sub n plus the summation from n equals 1 to y1 of a sub n minus or the negative terms, and then all the way up to the summation from n equals y of n minus 1 to y of from n minus 1 plus 1 to y of n minus 1 ace of n negative. So this might seem a little bit complicated, and the best way to explain this for me is probably to just give you a visual idea about what's happening over here. Okay, so let's say that this is the number I want to create, and let's say that I'm just beginning this process. Okay, so the first thing that I'm going to do is I'm going to sum up the first x1 terms to get to this point. Then I'm going to add an additional y1 terms to get to this point. Then I'm going to add an additional x2 terms to get to this point, an additional y2 terms to get to this point, an additional x3 terms to get to this point, and so on. Okay, so what's happening over here is that when I have added the first x1 terms, it's basically this part right here, n equals 1 to x1 of ace of n plus, and then I'm adding an additional y1 terms, but these y1 terms are coming from the negative part of the sequence. And then I'm adding an additional x2 terms, but now these x2 terms are coming from the positive sequence, or from the positive part of the sequence, or yeah. So in other words, or what I'm going to do is I'm going to sum up from n equals x1 plus 1. So this is like let's say I've already added up the first 10 terms. Now I'm going to add up another 10 terms. So I'll have to start with the 11th term and then go all the way up to the 20th term in this case to add up, or the 21st term in this case to add up another 10 numbers. So this is how the process is going to iterate. Every time I'm adding numbers, I'm not going to repeat numbers. So if I've already added up the first x1 terms from the sequence, from the positive part of the sequence, the next time I'm adding anything from the positive part of the sequence, it will start from the x1 plus first term. I'm not going to add up the x1 term again and again, because while that just destroys the purpose of the question, you need to make sure that every term is being added exactly once. So what this process above, what the process that I've outlined above over here, where I'm writing the general two iterations, what this is just saying is that this is just defining, in a more general way about what the general nth iteration is going to look like. Because remember, each iteration consists of two steps. The first step is to add up enough positive terms to exceed s, and then the second step is to add up enough negative terms to reach something that is less than s. And what this is telling us, what this general part over here says, is what is the general nth iteration going to look like. So if you just sub in n equals 1 over here, you're just going to get this iteration again that we just wrote, right, that I just wrote over here. And if you want to get the next iteration, or the next step, or what the next step is going to look like, all you have to do in this iteration over here, in this general the general formula for the nth iteration, is to just sub in n equals 2, and you're going to get what the second iteration is going to look like. So that's generally how it's gonna work. Okay, so now that I've done this, now to find the general iteration, now let's see what I can do next. And after this, it's just, the idea is just to recognize the following. Notice that after each step, after each iteration, to be more precise, after each iteration, or after each step in the iteration, I'm at a value that is either slightly less than s, slightly less than, or slightly more than s. So those are the only two cases, because the way I've defined my iteration is that I'm gonna go above s, then gonna come below s, above s, below s, and so on. So after each step of the iteration, I'm going to be either at a value that is above s, or that is slightly less than s. Okay, now what I'm going to do is I'm going to say let this iteration over here, so this is one of the iteration, and this is the second iteration, or so the second part of the iteration. So I'm going to say, in general, let the first part of the iteration where I exceed s, be u of n, and let the second part of the iteration, where I am below S be V of n. To be more precise, if I want to, just say what U of n is, U of n is where I've exceeded S, and this is the part where I exceed S. So I can say that U of n in general is just going to be the summation from n equals 1 to x1 of a of n plus the summation from n equals 1 to y1 of a of n negative plus all the way up to the summation from n equals x of n minus 1 plus 1 to xn of a of n plus, and v of n is going to be the summation from n equals 1 to x1 a of n, the same stuff, n equals 1 to y1 of a of n negative plus all the way up to the summation from n equals y of n minus 1 plus 1 to y of n of a of n negative. Of course, this is plus and this is also plus. Okay, so essentially, every time I do a step like this, I'm gonna be at a point that is greater than S, and every time I have a step of this form, I'm gonna be at something below S. But the more important thing to notice over here is that in each step, U of n or V of n is going to differ from S by at most ace of xn plus or ace of yn plus. Okay, why do I say this? Why is this true? Because once again, if you think about what's going to happen, let's say that I have been doing this process for a very, very long time, and now I have just added up xn minus 1 terms. So I'm at the point where I have added up ace of xn minus 1 terms from the positive sequence. So I have added x of n minus 1 terms from the positive part of the sequence, and I'm at something that is just below S. It can also be equal. It can also be equal to S. Doesn't matter. But if it is equal to S, the very next time I add something, it's going to be ace of xn plus, because that's the next term in the sequence of positive terms. And that will, let's say that brings me at this point. So the maximum amount that I can be far, or the distance between this point and S will be at most ace of xn plus. It can't be anything larger than that, well, because that's the largest value I can add. After that, my iteration will end, because that would be the least number of terms I need to exceed S at that point. So I will defer from S by at most ace of xn plus or ace of yn. So this should be negative ace of yn minus if I'm subtracting something. So if I've just subtracted y's of n minus 1 terms, I'm at something that is larger than S. Once I subtract y's of n, I'm going to reach something that is smaller than S, but it's going to differ from S by at most y's of n. It can't differ from S by something that is larger than y's of n, or the ace of y, or ace of yn, or theynth term in the sequence ace of n negative. It can't differ from S by more than that. Because if the previous term brought me, when I subtracted the previous term, if it brought me at S, then once I subtract an additional term, it's going to bring me at some point over here. And of course, I'm not going to subtract anything after this, because I'm already something at that is below S. But then what's this distance? This distance is ace of yn negative. So the largest amount that I can defer, or that I can be away from through this iteration, is ace of xn plus or ace of yn minus, or ace of yn negative, depending upon whether I'm subtracting the terms or I'm adding the terms. But notice that this can be rewritten by saying that u of n minus S is at most ace of xn plus, and v of n minus S is at most ace of yn negative. But also, one thing we also know is that since u of n is always something that is larger than S, and v of n is always something that is smaller than S, I can say that v of n, this relationship also needs to be true. V of n is always something that is less than S, and u of n goes right here. Okay. Now, the last step of this proof goes as follows. As we know, as the summation from n equals 1 to infinity of a of n is conditionally convergent, as this is conditionally convergent, by the necessary convergence test, I know that limit as n approaches infinity of a of n has to be equal to the limit as n approaches infinity of a of n plus, which has to be equal to limit as n approaches infinity of a of n negative, and all this has to be 0. So the sequence of positive terms has to converge to 0, the sequence of negative terms has to converge to 0, and the sequence of the entire sequence a of n also has to converge to 0. Accordingly, as n tends to infinity, let's see what happens to each one of these cases. Well, what happens is u of infinity, well, if I replace n with infinity, minus s in absolute value is going to be less than or equal to s. So all I'm doing is that I'm implying I'm applying the limit as n approaches infinity on both sides, and I'm gonna get v at infinity is, well, I'm gonna say that this is less than or equal to, doesn't really make a difference, but this is less than or equal to s, which is less than or equal to u of infinity. So this is true. This needs to hold, but well, together, this implies that if I let n approach infinity, u of infinity tends to s, and v of infinity also tends to s, because well, the distance between them approaches 0. So u of infinity also tends to s, and v of infinity also tends to s. In other words, s equals u of infinity, which equals v of infinity. So hence, what I can say is, hence, the sequence of partial sums, the sequence of partial sums defined by the process above, approaches s when n approaches infinity, where n is the number of iterations of the process. Okay, and now I'm pretty much done. I'm gonna say let alpha that maps from n to n be a bijection which creates the partial sums, outlined above. Okay, and then, as I've already shown, this sequence of partial sums as n tends to infinity is going to converge to s, where s is any real number that you gave me, and this completes the proof. So the proof is, of course, very, very long. Well, it's not very long, but it is quite long, and it's also a little bit complicated. But well, the harder part is really to understand. Personally, what I think is the hardest part is to understand this process of iteration. Like, how do you generalize this process? And it's not something that you're going to understand once you just look at it at first sight. You'll actually have to write out some more steps in the iteration. So, for example, what the only thing that I showed you in this video was the first step of the iteration, what the first step is going to look like over here. I would recommend that if you do not understand how I got this, general part of the iteration, you either refer to the PDF that I'm going to show below, because over there I've actually written out, the second part of the iteration as well. So what the next iteration is going to look like. So this is just the first iteration, and then you can get the second iteration, and then once you see the pattern, you can generalize that to the nth iteration, which is going to look something like this. This is the nth iteration over here. In general, this is the iteration that you are going to get after you have done n such iterations. So the reason why we in mathematics always write stuff generally is because, let's say if you weren't writing it generally and I asked you what's the 100th iteration, what you would have to do is you'd have to write out the first 99 iterations and then the 100th iteration, and then tell me, well, you know what, this is going to be the 100th iteration. But once you write down a formula for any arbitrary nth iteration, if I now ask you, well, what is going to be the 100th iteration, you can just replace n over here with 100, and you are going to get what the nth iteration is. To be a little bit more precise, I shouldn't have actually used n over here, because, well, it also appears in the term ace of n. I should have used something else. Should be plus over here, plus over here. Yeah, they are a little bit. Yeah. Okay. Yeah. Everything else is fine. Yeah, but it's okay. You could actually use q over here if you want to be a little bit more rigorous, or use q over here, because that will ensure that the reader is not confused about what exactly n over here represents. But since I've pretty much clarified that n represents the number of the number of iterations, it shouldn't be a problem. And then once you get the iteration, you just have to recognize the fact that since once you've written out the iterations more generally, you just need to recognize the fact that since the summation from n equals 1 to infinity of ace of n is conditionally convergent, as n tends to infinity, the terms in the sequence ace of n become smaller and smaller and smaller. They effectively just become 0, and therefore each time you apply the iteration, you get closer and closer to s, until eventually the sequence of partial sums that are created by this process of rearrangement of the natural numbers, or the rearrangement of the terms of the sequences of n, will converge to s, or it practically forces the sequence to converge to s. Now, one thing I want to emphasize over here is that over here I've assumed that s is something that is greater than 0. The proof is very, very similar. It's extremely similar if you assume that s is something that is less than 0. The only thing that changes is the order in which you're applying the iteration. So instead of adding up the terms first to get to something that is slightly larger or slightly smaller than s, now you'll be adding enough negative terms to obtain something that is slightly smaller than s. Then you'll add up enough positive terms to get something that is slightly greater than s. And then you repeat the same iteration, and every other part of the proof remains the same. Yep, and that's pretty much it for this video. I mean, this is a hard proof, so if you do not understand this proof, like if you do not understand what's going on, if you do not understand, some step in this proof, do let me know down in the comments below, and I'll try my best to explain it. Also, I would encourage you to refer to the PDF that I'm going to upload, in which I've actually written out the proofs completely rigorously as well, and see if that helps you better understand this proof. And yep, that's pretty much it. I'll see you in the next video.